Thank you for the introduction. So today I'll be talking about something that's a little bit different than what Brandon and Ricky talked about. And specifically, I'll be talking about meta-learning. And to motivate meta-learning, when thinking about how we might build generalizable models that can operate in the real world, I think we're often in a situation that looks like this, where our desired test distribution is much broader than the distribution of data that we may have data for. For example, in robotics, one of the fields that I work in, your trained distribution may be a lab environment, and your desired test distribution may be much broader, such as the real world, where you may encounter many different spatulas or many different kinds of environments. Or in computer vision, maybe your training distribution is ImageNet, and again, your test distribution is the real world, where these classifiers may not perform well across the board. So how might we try to extrapolate beyond our training distribution if we have trouble broadening our training distribution to the extent of what we'll be seeing at test time? Well, one way to do this is to try to build in structure into your model so that it can leverage that structure and generalize, use that structure in a way to allow it to generalize further. For example, you could build in compositional structure or symmetry like equivariance into the model to encourage it to generalize. Convolutions, for example, are one way to build in symmetry by saying that that data is translationally equivariant. Then the key question is, how do you actually build in the structure? One very natural approach is to try to build it in by hand. This is very natural because it seems like we're very good at generalizing, so maybe we can transfer our knowledge to the model. But I'd argue that we're actually really bad at building in the structure into models, just like we're really bad at building feature detectors. And we've seen this with kind of the history of computer vision when the performance on ImageNet got substantially better after the introduction of deep neural networks. So while we're really bad at building feature detectors and building in structure, we are really good at learning from data. And so the motivation behind meta-learning is, can we learn structure from data and then transfer that structure to new tasks such that we can generalize with very small amounts of data? So how exactly does this work? I'll briefly overview how meta-learning works, and then I'll talk about some of the challenges and some of our recent work that really pushes the boundaries of what meta-learning can do. So the way that meta-learning works is we may want to be able to learn from a very small amount of data. And one kind of very classic example of meta-learning is this few-shot classification problem, where we may be given one example of 5 different classes, as shown here. This is our tiny little training data set. And we want to be able to learn from this training data set such that we can classify new test examples, as being among one of the 5 classes shown on the left. Now, of course, if we train from scratch, this is completely impractical to be able to solve from only 5 data points. But what we can do is, if we have image data from other image classes, we can structure that data in a way that prepares us for this few-shot classification problem at test time. You can essentially structure those other image classes into mini train sets and test sets, and across these training classes, learn how to learn from each of these small data sets in a way that allows us to generalize to new test inputs. And then once we do this meta training process across many different tasks, then at meta test time, given a new task with new image classes, we can effectively solve the problem. Essentially, meta-learning is learning how to learn from small amounts of data such that you can generalize to new tasks. And in this example, the tasks are image classification tasks, but they could also be other machine learning tasks like reinforcement learning, imitation learning, and so forth. So that's roughly how the meta-learning training setup looks like. And one approach that kind of fits within the theme of this workshop is to embed a learning process, an optimization process inside the process of learning from our small training data sets. And in particular, we might start with some neural network, take our tiny training data set, run an optimization on this data set to get a new neural network, and then optimize this entire process such that when given a new image, you can output the correct label. Essentially, we're training these neural networks, training this optimization process, for example, the initialization or other aspects of the optimization like the learning rate, such that you can learn from smaller amounts of data. So this is kind of the key idea behind meta-learning. And one algorithm that I developed back in 2017 is model-agnostic meta-learning, What this algorithm does is that it learns a set of initial features that are particularly well suited for fine-tuning with small amounts of data, such that with one or a few gradient steps, you can generalize effectively. Okay, so that's a brief overview of meta-learning. And while meta-learning allows us essentially to lift kind of training and generalization from data points to tasks, we still need to make this assumption that the task distribution that we're meta-training on is the same as the task distribution that we are given at test time, or at meta-test time. And we often find ourselves in a situation where actually designing many of these tasks can be pretty challenging, and our desired meta-test task distribution, the task we want to be able to generalize with small amounts of data, is broader than the task that we are meta-trained on. And in particular, often we want to learn new tasks that are related to the meta-training tasks, but not necessarily draw an IID from the meta-training distribution. To think about this problem, we need to think about the word related. Like, how do we actually define whether a task is related and so forth? To do so, we're going to consider tasks as being related if they share a certain structure. And in particular, in the first part of this talk, we're going to be talking about structure that corresponds to equivariance or invariance. And we want to see if we can discover equivariant or invariant structure via meta-learning, essentially if we can discover symmetries in the data, and then transfer that structure to new tasks to be able to kind of transfer more effectively to tasks that may be a little bit different. And in the second part of the talk, we'll see if we can try to adapt a distribution shift in the data, specifically using the structure recovered by meta-learning. Okay, so first let's talk about whether we can discover equivariant and invariant structures via meta-learning. Now, the first natural question here is, does meta-learning already do this? And in particular, does the MAML algorithm, the model agnostic meta-learning algorithm, already allow you to discover a structure and use that when transferring to new tasks? Now, it's worth noting that MAML can learn initial features, an initial neural network that has a certain equivariance, simply by encoding that in the weights of the neural network. However, the gradient descent step may not actually preserve that equivariant structure. So while the initial features may be equivariant, the features learned in the second step may not be equivariant. Or the features learned after the gradient step may not be equivariant, may not share that structure. And so what we're going to try to do here is we're going to see if we can essentially decompose the weights of the neural network into a particular equivariant structure that preserves things like translational equivariance or rotational equivariance and so forth, decompose that from the underlying parameters of that network. Essentially, if we could do this, basically, we can update only the parameters in the error loop and retain the equivariance across the update step. Okay, so this may be a little bit abstract and vague, but hopefully it'll get more clear as I go on. And the first thing we want to look at is how our equivariance is actually represented in neural networks. And to do this, let's look at an example. So all of us should be pretty familiar with how convolutions work. And in particular, here's a visualization of a 1D convolution layer, where the input X is convolved with a filter W to produce the output Y. And the way this works is you take the dot product between the filter and the input, and you slide the filter across the input in order to produce the output. Now, this is one way to represent a convolution layer as this filter that you're sliding across the input. But another way that you could represent it is actually using a fully connected layer. And the corresponding fully connected layer looks like this, where the weights of the filter are actually repeated across the fully connected matrix, and the remaining entries are all 0. And then this basically corresponds to the identical function as the one on the left. Okay, so now that we have a mechanism, and actually it's worth mentioning that you can also do this with other things other than convolutions, such as other kind of rotational equivariant functions as well. You can always kind of construct a fully connected layer that has the same sort of equivariance as that original function. So now that we have this visualization, we can note that basically what convolution corresponds to is a certain weight sharing pattern and a certain weight sparsity pattern, where ABC is shared, like different parameters of this fully connected matrix are shared in different parts of the matrix. And so what we're going to try to do is we're actually going to try to reparameterize this fully connected matrix such that part of it is representing the weight sharing pattern and another part of it is representing those parameters, the ABC parameters. And in particular, the way that we can do this is we'll have our parameters shown in yellow and green. And this is just a really simple example with 2 parameters. And then we're going to represent this sharing matrix as U. And this sharing matrix is basically saying for each parameter in our fully connected network, for each weight in our fully connected network, which parameter is it going to use? And when we multiply this, this matrix times this vector, we'll get a vector of weights, and then we'll reshape that into a fully connected network. Essentially, this is a way to reparameterize, in this case, a fully connected layer, just a matrix, as something that is composed of a smaller number of parameters. Essentially a way to represent different ways of sharing parameters. And it turns out that we can actually theoretically prove that this reparameterization can directly represent decoupled equivariant sharing patterns and filter parameters. And we can prove this for all group convolutions for finite groups G. And this is pretty nice because this means that we can actually, this is a means to essentially decouple certain kinds of structure, in particular equivariant and invariant structures, where invariance is actually a special case of equivariance, and decouple that from the underlying shared parameters themselves. Note here in this example, the sharing matrix is discrete, it's only zeros and ones, but you can also represent this with continuous values to represent other forms of equivariance. Okay, so with this kind of decoupling, or with this kind of reparameterization of a fully connected layer, what we can do is essentially, when we're meta learning, the inner loop can basically only update the parameters V, such that when you take kind of your weight matrix W is represented by U times V. When you take your inner loop loss, you can backpropagate that only into V, keeping U fixed, such that after the gradient update, the equivariance in U is preserved, it's fixed, and the underlying parameters are what's updated for the data. And then in the outer loop, we'll learn both the equivariance U as well as the initial parameters V. So essentially, this is allowing us to learn certain equivariance patterns that we assume are fixed across all of the tasks in our meta training set, and therefore allow us to kind of learn that and preserve it for all of the tasks. Okay, so we refer to this as meta-learning symmetries by reparameterization, MSR, essentially kind of a reparameterized version of MAML. And with this method, we wanted to answer a few questions. Our first hypothesis is that with this approach, if we have translationally equivariant data, it should be able to discover the structure of convolutions. And so what we did is we generated synthetic data from a variety of different translational equivariance data. It was data that kind of had a vector of inputs, a 1D translate that is 1D, then a function that has a 1D translational equivariance and produces an output. And with this data, we ran the previous approach that I just described, as well as MAML with a fully connected network, a locally connected network, and a convolutional network. And what we found is that when we were measuring the mean squared error for these for new meta test tasks, MSR was able to achieve performance that's comparable to MAML with convolution layers, even though MSR was starting with a fully connected network. And of course, MAML with fully connected networks and locally connected networks performed worse than MAML with convolution networks because they don't have this, this equivariance. And further, we can show that we can actually visualize the kind of what it learns, the matrices that it learns, and it learns something that exactly looks like that matrix that I showed earlier with the particular sort of translational equivariance, with the weights copied over the matrix. Okay, so this is the first question we asked. The second question we wanted to ask is, can we actually discover something better than convolutions in situations where our data isn't exactly translationally equivariant? And so to do this, we generated synthetic data first with partial translation symmetry. In this case, the partial translation symmetry was a locally connected network where there was a large amount of sharing between the filters in the locally connected network, but not all of them shared. So we considered either one filter that shared for all of the locally connected network, which corresponds to convolution, as well as 2 filters that are shared across the locally connected network, and 5 filters that are shared across the locally connected network. And what we find is with 1, 2, and 5 filters, MSR is able to discover that symmetry, basically a symmetry that works well and achieves low mean squared error, whereas convolution is able to do well, MAML with convolutions is able to do it well in the k=1 case, but isn't able to do well in the 2 and 5 case because convolutions is making too strong of an assumption about the symmetry of the data. And likewise, locally connected and fully connected are making too weak of an assumption about the symmetries in the data. The next thing we want to look at is data with translation that is translationally equivariant, rotationally equivariant, as well as reflection equivariance. And in this case, we actually initialized MSR with a convolution network instead of with a fully connected network. And we found that MSR was able to outperform MAML with convolutions by learning this stronger equivariant structure. Okay, so this is pretty cool. And so far, this was all on synthetic data. The last experiment we wanted to look at is if we can learn symmetries from augmented data. Essentially, if we can learn in a way that essentially builds or bakes in the augmentation into the architecture or into the neural network itself. It basically bakes in those symmetries into the architecture. And so to do this, we have a very simple algorithm where we have a set of meta training tasks, any sort of meta learner, and a data augmenter. And for each task, we split it into a train set and a validation set, augment the validation data points, and then construct our new tasks using the original train set and the augmented validation set. And so what this is going to do is it's going to train it such that after it's seen original images in the training data set, it can generalize well to augmented images. Essentially, we're trying to bake in the data augmentation into the update rule or the architecture that the meta learner acquires. And what we find is when we compare MSR to MAML, almost no inner loop, a variant of MAML that only trains the last layer, as well as prototypical networks, MSR is better able to capture these kinds of equivariances in its learning process compared to these prior works. Okay, cool. So we're pretty excited about this in the sense that I think it provides a framework for understanding the interplay of features and structure in meta learning. And it specifically decomposes those two things, at least for equivariant and invariant structure, such that we can control which are being adapted in the inner loop and which are being shared across all tasks. Okay, so far we've talked about learning symmetries. And the goal of using kind of structure and compositionality and equivariance is actually to get better generalization. And we showed one form of better generalization previously, where we wanted to generalize to augmented data. But we also want to study a setting where we may have distribution shift from the training data to the test data. So can we adapt to distribution shift using the structure recovered by meta learning? So to do this, we first need to think about what kind of distribution shift we'll be considering. In this next work, we're going to be talking about group shift. And in particular, we're going to build upon previous work on group robustness that considers there's this categorical group variable Z that may be things like gender, race, some background scene, etc. And we're going to assume that we're going to know this group variable during training for each of the training data points. Then we're going to assume that our training data is drawn from this distribution and our test data is drawn from this distribution. So P of X and Y given Z is going to be the same between training and test time, but this underlying distribution over Z may change. And this can capture situations such as label shift and most forms of covariate shift. Now, one very popular approach for handling this kind of distribution shift is called group distributionally robust optimization. And essentially what this tries to do is to form an adversarial distribution Q of Z and optimize for the worst case distribution over Z, such that when you're given, maybe at test time, you're given a minority group, such as a minority race or a minority gender, you don't want to sacrifice, you want to get kind of the best worst case performance, even if that group is heavily underrepresented in the data. And this approach can enable very robust solutions to these kinds of groups. And it's also less pessimistic than adversarial robustness, which may try to essentially be robust to really any sort of perturbation of the image. Downside, though, is it is still somewhat pessimistic and often sacrifices average or empirical group performance in the process of being robust. So what we'd like to do instead is try to adapt instead of aiming for simply robustness. And in particular, we assume that we have a set of unlabeled images that represent the part of the distribution that we're in at test time. And our goal will be to try to essentially adapt to that sub-distribution. And we'll call this, and so we're assuming essentially that all of our test inputs at test time are available in a batch, all of our unlabeled test inputs, and these are all part of one sub-distribution. And we'll refer to this as adaptive risk minimization instead of empirical risk minimization, in the sense that we're going to be adapting at test time to the part of the distribution that we're in. And then the algorithm that we'll use will first construct sub-distributions of the training data and then train for adaptation to those sub-distributions. So the way this will work is at training time, we'll have all of our images, their corresponding labels, as well as their corresponding groups. We'll construct many different distributions from the group data such that we can sample a sub-distribution and then adapt that sub-distribution. And each of these sub-distributions will be constructed using group information. Depending on the application, we'll construct things in a slightly different way. We may construct a uniform distribution over different proportions of groups, or we may have a sub-distribution correspond to a group itself. Okay, so how do we actually train for adaptation to unlabeled data? For this, we need to essentially build a meta-learning algorithm that can adapt to unlabeled data rather than labeled data. To do this, we'll build upon previous approaches that essentially condition the network as context on the data. So in particular, our architecture will look like this, where we take unlabeled images from our subdistribution, then pass this into a neural network and aggregate this information into a contextual embedding of the subdistribution. We'll then combine this with the query image, which will be used to predict y hat, an estimated label for that query image. And then we'll compare that prediction with the correct label to perform the classification loss for the query image. Then we'll train this network end to end for a variety of different subdistributions that we sample from the data. So how does this do? So we compared adaptive risk minimization to empirical risk minimization, distributional robustness, and specifically a previous method that actually combined DRL methods with neural networks, as well as a solution that tries to upweight the groups to the uniform distribution rather than training on the empirical distribution of groups. So we experimented with a few different data sets. The first data set we looked at was very simple. We just took MNIST and different groups corresponded to different rotations of the digits. And we trained on a very skewed training distribution such that some rotations are much less represented than others. And what we found is that ERM and in other methods, essentially their performance drops in the parts of the distribution that are underrepresented, as we would expect. But our method, which is able to adapt to different distributions, to different rotations essentially, is better able to adapt to this sort of situation and achieves better worst case accuracy and average case accuracy. We also looked at two more experiments, one that is based on the CelebA data set, and one data set that is called Federated MNIST that essentially has different people writing different characters, not just digits, but also the English alphabet, so all the letters in the English alphabet. And what we find in both of these cases is ARM is able to achieve better worst case accuracy and average case accuracy in both cases, and is also able to achieve good empirical accuracy as well, and get close to empirical accuracy of ERM in the case of CelebA. And one of the things that's pretty cool about this federated MNIST setting is that you're actually adapting to new users at test time. And this is a bit different than what group robustness typically looks like. And one example of what this actually looks like in practice is, here's an example image at test time that the algorithm is given. ERM would just be asked to classify this as is, and it's a bit ambiguous if it's a 2 or a lowercase a. And however, if we give kind of the context of other digits written by that person, it's a little bit clearer that this is actually a lowercase a rather than a 2. And we find that ERM incorrectly classifies this as a 2, especially because 2s are actually overrepresented in the data set compared to lowercase a's. Adaptive risk minimization, when only given the 2 digits in the dashed black square, also outputs as a 2, whereas when given 50 unlabeled images, ARM is able to effectively and correctly classify this as a lowercase a. Okay, so to wrap up, I talked about how we might discover equivariant in an invariant structure via meta learning, and then use this when trying to transfer to new tasks, and show how this can essentially be used to discover certain kinds of structures like convolutions. And I also talked about how we can adapt a distribution shift using the structure recovered by meta learning, specifically looking at shifts in groups. I'd like to thank my students. If you're interested in learning more about meta learning, generalization, and so forth, I encourage you to check out my course. All the lecture videos are available online, and I'd be happy to take a few questions. Thank you.